Hello, algebra students. Today we're going to talk about equal distance uniform motion problems, a well-loved topic by all math students. With these problems, the rate and time may differ, but the two distances given will always remain the same. Because of that fact, all diagrams pertaining to these problems show equal distances, and therefore D1 is equal to D2 under all circumstances. Here is the fundamental idea you should all know. In all types of rate, time, and distance problems, the formula to use is rate times time equals distance. For example, 15 miles per hour times 2 hours, if you cancel, equals 30 miles. Now understand this concept because this is the basis for all of these types of problems. Check out a popular video in the description illustrating the necessity to understand this concept. Problem number 1. John drove to Mexico in 12 hours. While Mark drove to Mexico in 9 hours. At what rates did John and Mark travel at if Mark's rate was 2 miles per hour faster than John's? Now the first thing you do is draw a diagram, and since this is an equal distance uniform motion problem, the lines will be congruent. Since this is a video, I have some visual aids to help you understand the concept. Here are my 2 cars and an iPod stopwatch. Now if you watch closely, I will attempt to replicate a 9 to 12 hour event in 12 seconds. Now assign values from the problem to some variables. First of all, since this is an equal distance uniform motion problem, the distance John traveled is the same the distance Mark traveled. John made the trip in 12 hours and Mark made the trip in 9 hours. We don't know what John's rate is, but we do know that Mark's rate is 2 miles per hour faster than John's. Now we've turned a word problem into math, let's organize the information. Now we plug in the equal distances in the distance portion of the box, and the 12 hours and 9 hours in the time portion. Since we don't know what John's rate is, we use an appropriate variable, and for Mark's rate, we write John's rate plus 2. Again, this is an equal distance uniform motion problem. The distances are equal, and from the formula I mentioned at the beginning of this video, the rate times time must be equal to. Now we plug in the numbers and solve. So that would be 12 r sub j equals 9 r sub j plus 18 because of distributive property. Now we subtract 9 r sub j from both sides and we get 3 r sub j equals 18. Now divide both sides by 3 and we find out that r sub j is 6. The problem also asks what Mark's rate was, so we add 2 to that answer. So that means r sub m is 8, and those are our 2 final answers. Problem number 2. Eric ran at a rate of 9 miles per hour at 2 p.m. Addison started running at 3 p.m. and caught up with Eric to join him for dinner at 6 p.m. How fast did Addison run and how far did they travel from their initial start to the time they caught up with each other? Now we draw a similar diagram again. To the best of my ability, I will try and reenact the scenario. I don't have any dolls or figurines on hand, so I'll use these cars again. Yeah, that didn't work out too well, but you get the idea, right? Eric's rate is 9 miles per hour, and we need to solve for Addison's rate. When we're given times of day, we have to physically count the time elapsed within the interval. I like to count it on a clock in the same way you count it on a number line. And of course, the distance Eric traveled is the same distance Addison traveled. Let's organize the information into the box. We can plug in Eric's rate as 9 and Addison's rate with a variable, and the hours 4 and 3 for Eric and Addison's times respectively. And once again, the distances are equal. Because of that fact, the rates and times of each equation is equal to each other. Then we plug in all the values and divide both sides by 3, and r sub a is 12. And since we need to also solve for distance, we can simply multiply either Eric or Addison's rate and time together to get the distance. And that would be 36 miles in both cases. Problem number 3. Using his last puffs of steam, Thomas traveled to the station at a rate of 24 miles per hour. Due to the large number of ignorant onlookers, Thomas refueled and sped off back into Narnia at 60 miles per hour to hide. If it took him 3 hours longer to get to the station than to escape to Narnia, how long did it take him to get to the station? What is the distance between the station and Narnia? This problem is slightly different because there is only one object, but it makes a round trip. Still, the distances d1 and d2 are equal. I couldn't find Thomas, so I'll use this car. Watch closely at this extravagant presentation. If you happen to blink, I just wanted to show that Thomas's rate was slower on the trip there and faster on the trip back. And d1 is equal to d2 even in this case. Now we need to differentiate between the two distances. S will be the distance to the station, and n will be the distance to Narnia. These rates to the station and to Narnia are 24 miles per hour and 60 miles per hour respectively. We know that the time to the station is 3 hours more than the time to Narnia, but we don't know the time to Narnia. Again, both distances are equal. We put the information into a box. First, 24 and 60 go into the rate column, and t sub n plus 3 and t sub n go in the time column, and then the equal distances in the last column. As I have said numerous times already, the distances are equal, so that means the rates and times must also be equal. We plug in the values and find out that 24 t sub n plus 72 equals 60 t sub n because of distributive property. We subtract 24 from both sides, divide by 36, and we get t sub n is 2. But that's not the answer. We need to find the time to the station, which is t sub n plus 3, and the answer would be 5. Also, we need to find the distance, so we can multiply the rates and times together in either direction to get the distance of 120 miles. That's all that I have on this topic, and I apologize for erasing everything before you could look at it. Anyway, check out the video in the description. Thanks for watching.